So 25 people have joined. So we'll start today's session on the satellite communication unit 1, inclination changes, effects of sun and moon on the earth orbiting. So we have a sun at the right hand side as you can see in the pictorial diagram, and the earth is at the left side. As you can see, the earth rotates in its own axis. Around the earth, the moon is rotating in its own axis, and we are going to place satellites in space which revolves around the earth. So as you can see in the diagram that the equatorial plane, earth's equatorial plane has been inclined towards the moon at a 55 degree from the satellite, and always from the sun the satellite should be inclined at an angle of 23 degree with respect to the sun's equatorial plane of 7.3 degrees. Okay. So the plane of the Earth's orbit around the Sun, which is elliptic in nature, it is having an inclination of 7.3 degree to the equatorial plane of the Sun. So the Earth is tilted about 23 degree away from the normal to the elliptic. The Moon circles the Earth with an inclination of around 5 degree to the equatorial plane of the Earth. So due to the Sun's equator, the elliptic, the Earth's equator, and Moon's orbital plane around the Earth are all different. So a satellite in orbit around the Earth will be subjected to a variety of out-of-plane forces, which will tend to try to change the inclination of the satellites orbiting from its initial inclination. So the mass of the Sun would be significantly larger than that of the Moon, but the Moon is considerably closer to the Earth than the Sun. So you can see that the Sun is far away as compared to Moon. So for this reason, the acceleration force induced by the Moon on a geostationary satellite is about twice, two times as that of the Sun. So the net effect of the acceleration forces induced by the Moon and Sun on a geostationary satellite is to change the plane of the orbit at an initial average rate of change of 0.85 degree per year from the equatorial plane. So as when both the Sun and Moon are acting on the same side of the satellite orbits, the rate of change of plane of geostationary satellites orbit will be higher than the average. So when both the Sun and Moon are acting on the opposite side of the satellite's orbit, the rate of change of plane of geostationary satellites will be less than the average. So in order to increase the orbital manual lifetime of the satellite, for a given fuel load, the mission planners deliberately place a satellite planned for geostationary orbit into an initial orbit with an inclination. Next is the orbit determination. The orbit determination requires that sufficient measurements are made to determine uniquely the six orbital elements needed to calculate the future orbit of the satellite. Hence, they calculate the required changes that need to be made into orbit to keep it within nominal orbital location. The control earth station uses to measure the angular position of the satellites. So these earth station satellites are referred to as PTC and M. So T first is stands for telemetry, next is tracking, next command and monitoring. These are present on the earth station. This TTCM uh, can be contacted from the spacecraft or by using the large satellite sub-operators, as it is generally uneconomic to build an advanced TTCM stations within a few three satellites to control. The orbital effects in communications system performance is the next topic. First one is your Doppler shift. So for stationary observer, if you have studied your optical communication very well, and if you have studied your mobile communication very well, the Doppler shift you would have understood it in a better way. So for stationary observer, the frequency of moving radio transmitter varies with transmitter's velocity relative to the observer. So if Ft is the true transmitter frequency, Fr is the receive frequency, then Fr will be greater than Ft when the transmitter is moving towards the receiver, and Fr will be lower than Ft when the transmitter is moving away from the receiver. You can see that in this. So Fr minus Ft divided by Ft is equal to del F divided by Ft, which is Vt by Vp. Del F is equal to Vt dot Ft divided by C, which is Vt divided by lambda. So therefore, Vt is the component of the transmitter velocity towards receiver. Vp is the component of phase velocity of light. Lambda is the wavelength of the transmitted signal. Next is the range variations. Generally, when satellite revolves around the Earth, it, un- it undergoes some form of variation in its position during the cyclic daily variation. This variation in the position heads towards the variation in the range between satellites and the user terminal. So let us see an overview of the satellite. Satellite definition is that it is an artificial body placed in an orbit around the Earth to collect information or for information. An artificial body placed in an orbit to communicate with the Earth to collect some information or communicate with it. So this is the generalized definition for a satellite. A communication satellite is a radio relay satellite station in orbit above the Earth, which receives, amplifies, and redirects analog and digital signals carried on a specific radio frequency. The satellite communications play a vital role in the global telecommunication. There are two major segments of satellite communication. They are the space segment and the ground segment. So space segment you can see in the right hand side this time. This, this pictorial representation, which is the example of a space segment, and at the bottom left hand side you can see the pictorial representation of a ground segment. This is the satellite system. How the satellite how the satellite communication works. So we are the users. The users, mobile users or the landline users are being placed on the Earth. From there, the signals are being generated. Those signals are being sent to the terrestrial system and the surface of the Earth. So from the terrestrial system, the signals are sent to the Earth stations. The Earth stations receive those signals, then transmit it to the transmitting antenna with the uplink frequency to satellite in space. So the signal that is being received in the satellite is being repeated, re-amplified, and further send it to the Earth station through the antenna with the downlink frequency, where the location of this Earth station is at a different place. So from there, it is given to the terrestrial system, then it is given to the corresponding user who is using this technology or application. So you can have a view on the satellite communication block diagram. If you are having any queries, you can kindly type in chat box. Yes, is there any queries from your side? If there are no queries, I'll proceed further onto a small demonstration on how the satellite works. Okay, we will see a demonstration on how the satellite works, then we'll proceed on to the next slide of the next topic, which is about geostationary. So let us see how the satellite works first.
Satellite. A satellite is any object that revolves in a curved path around a planet. There are two major types of categorization when it comes down to satellites. One is natural satellite, and the other is artificial satellite. A natural satellite is any celestial body in space that orbits around a larger body. Satellites that are made by people and launched into orbit using rockets are called artificial satellites. Launching an artificial satellite. The launching a satellite into orbit involves two steps process. First, the satellite has to be taken to the desired altitude. Then, it has to be pushed off at the right velocity to begin and maintain its orbit. To launch a satellite in an orbit around the Earth, launch vehicle, such as a rocket or a space shuttle, is used. A launch vehicle travels straight up only for the first few seconds of its flight. A satellite launch vehicle is a multi-stage rocket. It also contains several smaller booster rockets. The boosters give the rocket its initial thrust during launch and carry the vehicle through the early part of the flight. As the fuel in the boosters is used up, the rocket fall away and the other boosters take over. Each time a booster is dropped, the vehicle gets lighter, so it can travel faster. When it finally reaches the proper altitude and speed, it releases the satellite into the orbit. How a satellite works. Satellite communication consists of three main components: uplink, satellite transponder, downlink. An uplink earth station or other ground equipment transmits the desired signal to the satellite. This satellite transponder amplifies the incoming signal and changes the frequency. This satellite transponder transmits the signal back to downlink earth station, and the ground equipment receives the signal. Satellite communication uses ground stations to send and receive microwave signals between artificial satellites, which are in orbit around the Earth. Types of satellite orbits. By inclination, there are three kinds of satellite orbits: equatorial orbit, inclined orbit, and polar orbit. Equatorial orbit. An equatorial orbit is when the satellite rotates in an orbit directly above the equator, usually in a circular path. It has an inclination of 0 degree. Inclined orbit. Inclined orbits are virtually all orbits except those that travel directly above the equator or directly above the north and south poles. The angle of inclination vary between 0 to 180 degrees.
This is how normal people search. Scroll down. Enter. Read the entire...
Polar orbit. A polar orbit is when the satellite rotates in a path that takes it over the north and south poles in an orbital pattern that is perpendicular to the equatorial plane. Polar orbiting satellites follow a low-altitude path close to Earth's surface, passing over and very close to both the north and south poles. The angle of inclination of a satellite in a polar orbit is nearly 90 degrees. On the basis of the altitude from Earth, the types of orbits are classified into low Earth orbit, medium Earth orbit, and geostationary Earth orbit. Low Earth orbit. Low Earth orbit satellites operate at a distance of about 160 to 2,000 kilometers above the Earth's surface. It takes approximately 90 to 120 minutes to circle the Earth. Medium Earth orbit. Medium Earth orbit is the region of space around the Earth above low Earth orbit and below geostationary orbit. The orbital periods of medium Earth orbit satellites range from about 2 to 6 hours. This satellite operates at altitudes between 2,000 kilometers and 35,786 kilometers above the Earth's surface. Geostationary Earth orbit. A geostationary satellite is an Earth-orbiting satellite. It placed at an altitude of approximately 35,786 kilometers directly over the equator, that revolves in the same direction the Earth rotates, that means west to east. This satellite takes 24 hours to orbit the Earth. Orbits are also classified into two types on the basis of the shape: circular orbit and elliptical orbit. Circular orbit. Circular orbit is the orbit with a fixed distance around the barycenter, that is, in the shape of a circle. This orbit has an eccentricity of 0. There are several types of circular orbits, and they include geostationary orbit, polar orbit, and equatorial orbit. Elliptical orbit. An elliptical orbit is the revolving of one object around another in an oval-shaped path called an ellipse. The eccentricity of an elliptical orbit is greater than 0 but less than 1. Sometimes these satellites are closer, and at other times they are farther away from Earth. The closest point a satellite comes to Earth is called its perigee. The farthest point is the apogee. The most common example of elliptical orbit is highly elliptical orbit. Types of artificial satellites. Navigation satellite. A satellite navigation system used to determine the ground position of an object. It determines the geographic location of ships, aircrafts, or any other object. It is also vital to military forces. It is often used for gathering intelligence used for military purposes or as a military weapon. The major satellite navigation systems. The navigation satellite system with global coverage is called Global Navigation Satellite System or GNSS. The United States was the first country to introduce satellite technology with the Global Positioning System or GPS. Another ambitious global navigation satellite system aside from GPS in development is the Galileo system in Europe. Russia also has its own satellite system, called the Russian Global Navigation Satellite System or GLONASS. In China, there is the Beidou Navigation Satellite System, which will consist of more than 30 satellites. There is the Indian Regional Navigation Satellite System or IRNSS in India. Lastly, the Quasi-Zenith Satellite System or QZSS is Japan's satellite system, which is similar to a GPS satellites with some slight variations. Weather satellite. Weather satellites are primarily used to monitor the weather and climate of the Earth, to predict daily weather conditions, such as temperature and rainfall, to monitor how weather conditions, like storms, hurricanes, cyclone, tropical storms, develop and change over time. Communications satellite. The communications satellite is a satellite that transmits the signals such as telephone, television, radio, internet signals over long distances. If you do like my channel, please subscribe, comment, share the videos to your friends and like them.
So I hope you would have enjoyed and understood the basics of a satellite, the animation. So any queries you can type in chat box. If there are any queries, I'll address it or we'll proceed further. Okay, since no queries, thank you Mukesh Sai for your valuable feedback. We'll proceed on to the next slide, which differentiates how the satellites have been classified into. So, uh, the satellite will follow a path around a planet, which we define it as an orbit. So, these have been classified into two broadly into two, which is non-geostationary and geostationary, as you have seen in the animation. So, what is this non-geostationary? Non-geostationary were the earlier satellites that were used for communicating with the Earth, which were placed in higher orbits. Uh, so, this satellite communications used satellites in non-geostationary, low Earth orbits due to the technical limitations of the launch vehicles in placing satellites in higher orbits. These were called as non-geostationary. So, this non-geostationary were classified based on the orbital planes as polar orbit, equatorial orbit, inclined orbit, as we have seen in the pictorial representation. So, polar orbit is that the satellite moves from pole to pole and the inclination is equal to 90 degrees. In equatorial orbit, the orbital plane lies in the equatorial plane of the Earth and the inclination is zero or very small. In the inclined orbit, all orbits other than polar orbit and equatorial orbit are called inclined orbits. If the orbiting is done along the equatorial plane of the Earth, it is equatorial orbit, where the inclination is zero. And if the inclination is 90 degree, such that it moves from pole to pole, North Pole to South Pole. If the orbiting is done, it is polar orbit. Other than these two, if it comes with an angle other than 0 degree, 90 degree, it is called as inclined orbits. So the advantages of these non-geostationary orbits are that it requires less booster power, le- less delay in transmission path, reduced problem of echo, which is suitable for providing service at higher latitude, lower cost, which is bound to it is built and bound to launch satellites in non-geostationary orbits. So there are some disadvantages in non-geostationary, which is complex problem of transferring a signal from one satellite to another, less expected life of satellites. This requires a frequent replacement of satellites compared to satellite in geostationary orbits. Next, we'll see the geostationary orbits. There is only one geostationary orbit possible around the Earth, which is lying on the Earth's equatorial plane. The satellite orbiting at the same speed as the rotational speed of the Earth on its own axis. Advantages of these geostationary orbits is that it is having a simple ground station tracking. The It gives a constant range of frequencies. It has a very small frequency shift. And the disadvantage is that we cannot cover the polars. North poles and south poles cannot be covered using this. There would be a larger free space loss. The transmission delay is in the order of 250 microseconds. So, any queries in the geostationary and non-geostationary orbits. Next, we'll move on to the look angle determination. So, in order to know the look angle determination, first of all, we need to be familiar with the latitude and longitude. So, latitude is the measure of angular distance of a place north or south of the equator. So, it is measured with 180-degree imaginary lines that form circles around the Earth east-west parallel to equator. So, the equator will be having 0-degree latitude. Next is a longitude. It is a measure of angular distance of a place east to west of Greenwich meridian. It is measured with 360-degree imaginary lines that are around the Earth vertically up and down, which meet at North Pole and South Pole. So the Greenwich meridian is having 0-degree longitude. So this you all are familiar very much. So now let us see what is this azimuth angle and this elevation angle is. So the azimuth angle is the compass direction from which sunlight is coming. The azimuth angle is like a compass with north degree, with north having 0-degree and south having 180-degree. So azimuth angle is the compass direction from which s- sunlight is coming. Next is elevation angle. Elevation angle is the angular height of the sun in the sky measured from the plane. And these two are called as the look angles. So the coordinates to which an east south must point to communicate with the satellite is called as the azimuth and the elevation angles. Next is the look angle. The coordinates or the angles to which Earth station antenna must be pointed to communicate with the satellite are called look angles. This is a combination of both azimuth angle and the elevation angle. So there are some few steps to find the look angles. One is you need to find the central angle, which can be formulated by a formula shown in this. We need to find it with a formula. For that, we need to find the satellite's latitude, Earth station latitude, satellite longitude, Earth station longitude. So, in order to find the central angle, cos of central angle is equal to cos of Earth station latitude into cos of satellite longitude minus the Earth station longitude. That becomes your look angle. Then the elevation angle can be found out by tangential inverse of cos of central angle minus sine of the angle between the earth station longitude and the earth station latitude. So then we'll be finding the intermediate angle. The intermediate angle is the tangential inverse of this latitude angle minus the longitude angle divided by sine of the latitude angle. Then we can find the azimuth angle determination with reference to the earth station. In northeast, the azimuth angle will be equal to the intermediate angle, whereas in northwest, the azimuth angle will be equal to 360 degree minus the intermediate angle. In southeast, if a satellite is present, the earth station, the azimuth angle is equal to 180 degree minus the intermediate angle. When it is present in southwest, the azimuth angle is equal to 180 degree plus the intermediate angle. This is what which is shown in the diagram. So in order to calculate the look angle, we need to go for 6 orbital elements. One is the calculate the orbit from these orbital elements, defining the orbital plane, locating the satellite at time t with respect to the first point of axis, finding the location of the Greenwich meridian related to the first point of Aries, and using spherical trigonometry to find the position of the satellite relative to a point on the Earth's surface. Next is the satellite coordinates, as I said, the subsatellite point, latitude LS, longitude small ls, earth station location LE, longitude LE, calculating the angle at earth center, which is between the line that connects the earth center to the satellite and the line from the earth center to satellite earth station. Look angles which are the azimuthal angle and elevation angle. Azimuth angle is measured eastward from geographical north pole to the projection of the satellite on a path horizontal plane to the earth station. Elevation angle is measured upward from the local horizontal plane at the earth station to the satellite path. Is there any queries in the azimuth angle, look angle determination and the limits of visibility? If there are any queries, kindly type in chat box, because the next topic that we are going to see is completely different, which is solar eclipse. So I'll give you some 5 or 6 minutes of time. Any queries, kindly type in chat box. We'll resolve that, then we'll proceed on to the solar eclipse.